Much for the kind introduction, and yeah, thanks for accommodating for the remote talk as well. Sorry, because of scheduling conflict, I'm not able to join in person. But yeah, today I'm going to like share some of our recent research efforts on efficient AI in the era of large models. So without a question, we're in this era of scaling, right? The beginning of this is pretty much like people observe there's empirical scaling law with more compute, with more training data, and also larger model size, we're able to get better and better performance on different tasks. But the problem of that is that it follows a power law relationship. So that means if you want to get a constant improvement in the performance, you need to get tremendous amount of more compute in order to achieve that. So because of that, over the past 1 decade since the transformer paper, the model size has actually grown tremendously by 4 orders of magnitude. On the other hand, the hardware side is also making a huge improvement. On the GPU compute, we get like 100x more compute on the hardware now. But you can see there's clearly a gap between the model size and the compute. Thinking about the memory capacity and also the memory bandwidth, the gap is even larger. For the memory capacity, we get a little bit more than 10x over the past decade. For the memory bandwidth, we get just about like 10x, right? So how can we bridge this gap, ever larger gap between the demand for and supply of compute? So that's kind of the focus of our group's research. So our research focuses on like designing algorithms and systems to bridge this gap. On the algorithm side, we think about how we can find new algorithms to approximate and basically use less compute to without hurting the model's performance. While on the system side, we worked on provide the proper system support in order to translate the theoretical savings into practical speed up on the hardware. We also need to like co-design between the algorithms and system to deliver the best performance possible. So for this talk, I will like focus on answering 2 questions in efficient AI for language models or vision language models. So on the one hand, I want to answer like how we can accelerate the autoregressive decoding, which is one of the huge bottleneck of large language models because it's token by token generation. So I will talk about 2 solutions to this problem. One is on parallel decoding using DFlash, or better quantization scheme by using ParallQuant. And the second question I want to answer is like how can we accelerate long context profiling and decoding, especially in the context of multimodal language models. So I will talk about our work called Sparsity using contextual sparsity. So let me begin with DFlash. So a little bit of background here. Autoregressive language models are kind of the standard right now, but the problem of that is you generate generate the output token by token, so it's sequential and memory bounded. So that leads to like slow inference. There are different approaches to kind of solve this problem. One is using diffusion language models so that you can generate multiple tokens at a time. But at the moment, most of the diffusion language models usually suffer on the accuracy side. The more tokens you generate in parallel, usually the lower accuracy you will get. Another types of approach to solve this problem is using speculative decoding. The idea of speculative decoding is that in parallel to the original large target model, you also pair that with a small draft model. So the idea here is that you use the small draft models to speculate into the future, to guess a few tokens into the future, right? And then always you use the target model to verify the autoregressive generation from the draft model. So because of that, you're always guaranteed to get exactly the same output compared to original model. But the problem of the previous state of the state-of-the-art speculative coding is that they're not efficient enough. So for DFlash, we want to find a better approach for speculative coding while utilizing all the new advancements from the diffusion language models. So kind of doing a little bit of analysis of previous autoregressive drafting models, because it's for the draft models, they're inherently sequential decoding. So you can see on the right-hand side, the blue bars, right? Eagle 3, that's the previous draft model. With more draft tokens, the cost actually grows linearly with the draft length, right? Basically 4 to 8 to 16, you get like you double the draft latency. Because of that, you can only use a very shallow draft model, so it's limited by the capacity. Well, if you use actually DFlash, basically use block diffusion as the draft model, because you benefit a lot from the parallel decoding, so the cost is actually insensitive to the draft length. So you can see on the right-hand side, across different number of draft tokens, the cost of like diffusion-based drafting models pretty much stays like flat. And because of thanks to this, you can actually afford a larger and also deeper draft models and can lead to higher acceptance length. So using diffusion models for drafting is actually not as trivial because there are actually some previous work on exploring the same idea. Uh, the problem is usually like either you use the large draft models, but they are not practical because the cost of drafting is actually very high, or you use the small diffusion draft models, you can only achieve moderate acceleration due to the capacity limit. So what we found is there's actually a free lunch in the target model because the target model is actually very large. It actually knows the future already, right? So the idea is like we can obtain the information about the next few tokens from the target model using the target model's hidden states, and inject those hidden features from the target model into the draft model using the KV cache. So implementation wise, during the inference time, basically we first use the the target model, and then extract the hidden states from a few layers in the target model, and then just feed that as a KV cache, kind of a prefix KV cache into the target model. And then we just leverage bidirectional attention, kind of the same as the diffusion language model, to draft a few tokens, the entire block into the future. And then finally, we use the target model for verification. During the training time, it's kind of also similar, but basically you select a few anchor points in the draft sequence in the output sequence, and then use that to teach the model to speculate into the future block. So you need to carefully kind of design the attention mask to make sure you don't have any information leakage during the training time. So we applied like the original for the original DFlash, we tested on the Quant 3 model. So here we like evaluated both the acceptance length and also speed up we can achieve. So the original Eagle 3, you can achieve around like 3.5 up to 4 acceptance length, and for the speed up is like more or less around like 2x. And for DFlash, we're able to push the acceptance length way higher to all the way to around 8. And for some benchmark, we can get like 5 to 6x speed up. Also depends a lot on the data distribution, because for speculative coding, for more structured data, you can always get better like speed up because it's easier for the model to speculate into the future. So here, usually empirically, we found for math and coding benchmarks, you are able to push the acceptance length to uh, quite high. For example, GSM-AK, Math 500, AIME, right? These are the math benchmarks. And human eval, MBPP, live code bench, these are like coding benchmarks. While on chat benchmarks, usually is more or less capped at a let's say like 3x speed up, because like for human conversations, usually high entry fee, so it's harder for draft model to speculate as well. We've also tested across different concurrency on different models from 4B, 8B to 30B, and also across different concurrency from 1, 4, 8 all the way to 32. And we're able to deliver pretty good speed up across all different settings. Recently, we've also extended DFlash to larger models like Kimi, Minimax, like GLM, like those large models, and we can also deliver similar speed up as well. So let me show some like demos of DFlash. So this is kind of a prompt of a math problem. The left-hand side is the autoregressive model. The second one is the block diffusion model, SDAR. The third one is Eagle 3, and the last one is our DFlash. So you can see like for block diffusion, it's able to like decode a bit faster than the autoregressive model, but the problem of that is actually lossy. For Eagle 3, it's also able to accelerate it losslessly, but the speed up is somehow capped. While for DFlash, on this example, we're able to deliver 8x speed up, while delivering exactly the same output response compared to the autoregressive model. We've also integrated that into SGLong and VLM. So here we tested with SGLong on across like different types of tasks, from coding to explanation to reasoning to writing tasks. And we are able to deliver consistent speed up here. And here's another demo we applied to coding. Basically here we used the DFlash accelerated coder model to help us build a demo for DFlash. So left-hand side is the Qwen3 coder model, right-hand side is with DFlash. And you can see for coding specifically, it's able to significantly accelerate the decoding speed. So here DFlash has already completed, while the original autoregressive model takes like twice as long to complete here. And you can see here is the demo built by the model. Again, here left-hand side is the accelerated version, right-hand side is the autoregressive drafting model. And we also apply that to the open cloud as well. The left-hand side is Qwen 3.5 autoregressive model. We also tested with its native multi-token prediction heads, and right-hand side is our DFlash here. So here is we are using like open cloud to help us like just take a look at our GitHub and to see whether there's some issue it can just solve. So it's able to deliver like around 2x speed up compared to MTP, and a pretty large speed up compared to the autoregressive decoding here. All right, so that's a very high, like quick overview of like parallel decoding. Then I'll also talk about the other solution, right, to how to accelerate autoregressive decoding. Because thinking about the memory, like the reason why it's memory bound is because we only decode one token per forward pass, but it requires to load the full weights, right? Very few flops, but have very heavy like memory traffic. And that leads to very low arithmetic intensity. So quantization can also solve this problem by basically loading less for each of the compute. So quantization converts values to lower like bit widths, and weight quantization specifically reduces the memory traffic and then increase the arithmetic intensity, making the workload like less memory bound towards more like compute bound regime. So for previous like language model, large language model quantization, it can be pretty much formulated by this. So basically you have here's a linear layer xw plus b, and you apply some transformation to the weight, and then apply the inverse of the transformation to the activation x here. And for weight-only quantization, then you apply the quantization on top of the transformed weight. For weight activation quantization, then you also apply quantization to the transformed activation as well. So the reason why we want to apply some transformation to weight and activation is because empirically, there are like outlier channels in the weight matrices, right? So the hope here is that if we can design an appropriate transformation, we can suppress the outliers so that the transformed weights are much easier to be quantized compared to original weight. So we can then like quantize TW instead of the W. So there are a few like common transformations people have designed. For example, like channel-wise scaling. So the idea is basically scale some of the channels to be larger, some to be smaller, like some representative work, including like smooth quant AWQ. We can also use rotation. For example, here we can apply some orthogonal like transformation T, like spin quant QTIP here. So in this work called PyroQuant, our goal is to design a new transformation that is like first more expressive compared to the channel-wide scaling, and also more adaptive compared to like some fixed like randomized transformation, and also be more flexible so that it can be applied to any weight matrices as we want. So by more expressive, so the motivation here is that AWQ is actually very like very strong in like preserve the salient weights, but it's very effective, but it's also not enough, especially when you apply that to like a long decoding sequence, because for long horizon reasoning, it's very sensitive even to accumulation for small errors. So you can see tested on like some math benchmarks, the accuracy drop is actually quite significant on some benchmarks. So the solution here is that like channel-wide scaling itself is not sufficient, so we also need to apply rotation. And rotation helps to align the values at token dimension. Channel-wise scaling evens out the magnitude. The second property we want is we want it to be more adaptive. For rotation, previously a very commonly used rotation transformation is called random Halma transform, RHT. So it's kind of fixed, although it's randomized. So it's not optimizable, like cannot be like specialized optimized for each of the weight distribution here. So the solution here is that we want a learnable like rotation, right, rather than some randomized fixed rotation for to even out the outliers here. And the third property we want is we want it to be more flexible. For example, like previously, full rotation, because it's very expensive, previously like some work like spin quant, they will try to find some places that you can actually merge that rotation into the nearby weight matrices, right? So that you don't need to actually pay that cost online. But you don't really have that many like opportunities to have foldable or mergeable rotations. So we want to break that mergeability constraint so we can apply the transformations everywhere we want. But because of that, we need to apply the efficient, like the transformations online. So it has to be very efficient. And the opportunity we found here is that full rotations are very effective, but they're also very redundant, right? On the right-hand side, you can see compared to channel-wide scaling, rotation does help improve the output error, reduce the output error. But if we only keep the top 10% most important rotation pairs, we're also able to pretty much capture like most of the benefits you can get from rotation, right? So you don't really need all pairs of rotation. You probably only need the most important, like let's say 10% of the rotation to improve the performance here. So here we design we want like all three properties here. So we designed a new transformation called scaled pairwise rotation. The idea here is that instead of using matrix multiplication for rotation, we use a sequential, like a sequence of like Givens rotations. So that's pairwise rotation, only rotating across between those most important like kind of pairs of channels. And then we enable like parallel execution by adding some independence requirements on the rotation. So basically in one round, if one channel is rotated with another one, it will not be included in any other channel like rotation pairs here. And then we further combine that with channel-wide scaling to further even out the magnitude. So let's take a look at some experimental results here. We tested on Quint3 models on like different math benchmarks. So basically compared to AWQ, we are able to pretty much recover most of the accuracy loss on those long horizon reasoning, math reasoning benchmarks, while only adding a little bit of overhead compared to AWQ, because we do need to apply rotation online. So that's kind of, there's some overhead we need to pay. But because how we design those rotation to be very efficient, so the overhead is actually quite manageable here. So here's a demo. We deployed the parallel quantized model on NVIDIA DGX Spark. So left-hand side is unquantized model, BF16. The middle one is AWQ. The right-hand side is parallel quant. So you can see in this example, like in terms of the decoding speed, it's almost the same as AWQ, but we actually decode a bit fewer tokens compared to AWQ. So it's actually a little bit faster and also delivering the correct answer here. We also like deploy it onto Apple Silicon locally on like MacBook for some agentic use cases. So here, for example, like we use the Qwen 3.54B model to, for example, check out the website of our lab. And then like checking like which projects are interesting, right? And then like asking something about the project. So you can see you can run those fairly powerful models locally with quantization. And also for those two local agentic use cases, because it's long decoding with reasoning. So like preserving the quantization accuracy is actually quite important for those use cases. All right, so that concludes kind of the first question, like how we can accelerate memory-bound autoregressive decoding to approaches parallel decoding or better quantization. Then I will quickly talk about how we can accelerate long context perfilion decoding here. So for vision language models, one key bottleneck is actually we have a lot of visual tokens generated by processing either images or high resolution images or long videos. But the opportunity we see here is that high sparsity does exist in VLM inference because not every token is equally important. But the bottleneck here is that there lacks a unified recipe for how to effectively prune tokens in vision language models. So for sparse VLA, we decouple the sparsity in the prefilling and decoding stage. During the prefilling stage, the vision token pruning must remain strictly query agnostic in order to ensure that you can answer questions in the later rounds. Because if you actually prune tokens here based on the first request, and then for the second request, you might need like tokens, visual tokens, different vision tokens, you might not able to answer the questions anymore. So here, during the prefilling stage, we use some saliency-based metric, just calculating the attention scores across different tokens to figure out which vision tokens are in general not as important compared to the other tokens. While during the decoding stage, we can do a query-aware retrieval here. So basically, after prefilling, you already have a way smaller KV cache because of the pruning. And during the decoding stage, now you have the request. And based on each of the requests, you can retrieve the relevant tokens from the visual KV cache, right? So that way you can significantly push the performance to more compute bound and avoid permanently removing any information that could be important to any other queries here. So I'll skip some results here. So we tested our sparse VLA token pruning methods on like different image benchmarks and also compare that to different token pruning methods. So here we normalize the accuracy to 100% for the original unpruned baseline. So basically, if you're able to achieve 1.0, it's basically the same performance as the original unpruned model. So here on average, you can see on the bottom right here, on average, we're able to preserve 97% of the accuracy across different image benchmarks. And also it's way higher compared to the other baselines here. We also tested on the video benchmarks because for videos, you usually have way more redundancies. So here we are able to achieve more than 2x speed up compared to the improved baseline while preserving like the accuracy across different video benchmarks across different models from Qwen 2.5, Qwen 3, intern VL 3.5. And here's a demo, this is a physical AI demo. We used the Cosmos Reason model to give predictions based on a video shot by the robot, asking questions like whether it can execute the task specified in the instruction. And on the left-hand side is the original unpruned baseline, and on the right-hand side is with the our sparse VLA. So we are able to achieve 2x speed up on those video benchmarks while delivering the same performance here. All right, so to summarize a little bit, so for this talk, I cover two topics here. One is like how we can improve the memory bottleneck for autoregressive decoding, and on the other hand, like how we can leverage sparsity to accelerate long context prefilling and for decoding. So with that, I would like to conclude the talk, and yeah, thanks for listening.